All right, fantastic. Thank you, Paul, for inviting me, and thank you everyone for coming today. I'm excited for sharing this project. In fact, this was something that came about during my time at the Los Alamos Quantum Computing Summer School back in 2021. I was able to do this project with a few different people, namely Matthias Johnson, who was one of the other students in the program with me at the time, as well as postdocs Frédéric Savage and Martine Larocca, who helped for doing computer simulations and helping put the project together, as well as my two mentors, who really helped kind of setting the scene for the project and giving guidance along the way in WUCOSH and to me. So today my presentation is about quantum annealing without wasting time, because as many of you, I guess, in this seminar series know, is quantum annealing is a very useful algorithm for getting into particular quantum states, but the amount of time it takes can be quite lengthy. And so we want to, what we were trying to do in this project is see if we can reduce this time using certain techniques. So that's what I'll share with you today. Okay, fantastic. So if we start off by thinking about a quantum states Hilbert space, sort of like what I've drawn here on screen, the idea of quantum annealing, at least how I think about it, is fairly simple. We start with two things. One is some Hamiltonian that we want to go into its ground state. So I've shown it here on screen. Imagine it's located somewhere here in the Hilbert space. So this problem Hamiltonian could encode, I guess, a bunch of things. Usually, at least the way I've seen it, is encoding solutions to some classical optimization problem, or maybe some combinatorial optimization problem, things like satisfiability, or probably some other graph theory-esque problems, usually NP-complete sort of problems we care about. But I guess it could also just encode some Hamiltonian that you want to study the ground state of. So there's this as well. So this is kind of the way that some people port classical, try to make a quantum algorithm that solves classical problems using this quantum annealing approach. So this is one part of the algorithm, one ingredient. And then the other is some ground state that we can start in, or some quantum state that we can start in. So usually we use something called the driver Hamiltonian, and our objective in quantum annealing is to go from one ground state to the other. So, okay, again, I'm going to go through this. I'll go through this fairly briefly, since at an annealing seminar, I imagine that a lot of people already know parts of this story, but just to kind of graphically show this, we can start off and say the ground state for this driver Hamiltonian, and what we want to chart a path to the ground state of the problem Hamiltonian. In the standard paradigm for quantum annealing, at least the ones that I've seen, usually what people do for this is they look at something called the total Hamiltonian. So some kind of linear interpolation, say, between our driver Hamiltonian and our problem Hamiltonian. The idea is that we can then go from one ground state to another of this instantaneous Hamiltonian. And if we do this sufficiently slow enough, we can actually end up in the ground state for our problem Hamiltonian, solve our problem. And the way that we know we can do this is due to the adiabatic theorem. So this is kind of like the workhorse for this algorithm, which tells us that if we go kind of slowly enough along this path, we can make sure that we end up in the ground state for our problem Hamiltonian. The key thing, though, is that when we actually care about doing quantum annealing for many of these problems, we don't really mind what's happening in the middle here. What we care about more is, can we get to the end? Can we get to the ground state of the problem Hamiltonian? And so this is kind of the setup for the project that I'll share with you today, is if we forget about what's happening in the middle, can we just focus on getting to the ground state for our problem Hamiltonian, solve that particular problem. And so just to give a little bit of an illustration, it kind of goes really slow to do this trajectory if we're just using the standard paradigm. And so this is like the small issue with quantum annealing, is that it can be really slow. More quantitatively, what I mean by really slow is just the scaling of the annealing time with the system size tends to be exponential. So this is bad because, well, if we're imagining trying to solve a classical problem, well, we can just solve it classically using exponential time or resources versus using a quantum computer at all. So like I said, the idea here is, can we go off the path? Can we start from our ground state for our driver Hamiltonian and then go off path, but faster, and get to our ground state, such that we can, say, measure the ground state for this problem Hamiltonian, or get some basis state of this ground state with finite probability. That's really our hope. Okay, so that's the setup for what I want to talk to you about today. And now I'll just share a little bit of more of the technical side just to set up before I can share with you the results. I promise I do not have a lot of equations, so I don't know for this seminar series if people tend to be like equation heavy or not. Mine will be equation light. So this might be a good thing for some of you, and maybe others might not be as fun, but we'll live with this. So just to set up my notation, the kind of annealing that I have in mind has some sort of Hamiltonian, time-dependent Hamiltonian that looks like this. So there's both the driver Hamiltonian HD and the problem Hamiltonian HP. And then we have an interpolation between the two that happens, but instead of just a linear interpolation, we actually have some function A of t. So this is going to control what happens for the annealing process. And so there's like for the standard annealing, if we're doing standard linear interpolation, then this A of t would be something like the function t over some annealing time. And then you can go from so then you can go from time equals 0 to time equals the annealing time, and you'll go from one Hamiltonian to the other. What we want to see is, can we do something different? And yeah, in particular, can we optimize this function, this A of t, such that we end up in the problem Hamiltonian's ground state? So this is really what we wanted to do. In particular, when we start talking about optimizing this A of t, well, A of t is a function. It has some restraints, like, for example, we want at the end of the annealing time that this function is equal to 1, so that we don't have the driver Hamiltonian in this expression anymore. But other than this, there's like a lot of freedom as to what you want to choose for this A of t. To make things somewhat simple, what we looked at, in fact, were piecewise linear functions. So the idea here is that the piecewise linear functions, if you make the pieces small enough, you could kind of approximate other functions. And it also made it kind of simpler for doing some of the other analysis that we did here. But this is kind of the base template that we looked at for these A of t's. And I'll show you what these look like in a few slides down, so that you can get some more of a sense of what's happening. So this is really our starting point here. And the figure of merit that we're going to take is just at the end of the annealing, which I've shown here with a capital T. We want to look at the energy of the state. And the goal here is going to be to get as close as we can to the true ground state energy of the system. Now, this is something you don't have access to necessarily for like a general problem Hamiltonian. For us, we do, because we were studying a particular model where we could analyze this no problem. But yeah, this was what we chose as our figure of merit for doing this optimization. And in fact, we have this figure of merit with some tolerance. So we define this tolerance C, which is like a fraction of the gap between the ground state and first excited state of this problem Hamiltonian. And so as we make this fraction smaller, we get more. We have a tighter and tighter tolerance towards being at the ground state energy for our output state. So this is sort of how we've set this up. Now, these are all technical, a little bit more technical details for like how we do the annealing, or how we choose if a particular AFT function, or what I'm going to call the schedule, looks good. But yeah, this is just to keep in mind. Okay, so just to recap before I actually bring you into the particular model that we studied, there's kind of two steps of this process. So the first step is like an inner loop of our algorithm, or of our optimization, which is for a fixed annealing time, can we find or optimize this AFT such that we get close to the ground state that we want? So that's the first thing. And then we have an outer loop around that, which tries to optimize not the AFT anymore, but the T, the capital T. So we want to find in particular the smallest annealing time we can get. And so the idea is that if you put these two loops together, eventually what we can do is we can find how this annealing time T min scales with the system size. And our hope basically is that we can do better than the standard like linear interpolation for quantum annealing. In our model, it turns out that this scaling would be exponential in the system size. It has to do with there's this vanishing gap between the ground state and the first excited state during the annealing process. And so this would typically take an exponentially long time if we do this like standard linear interpolation. But in our case, we want to see, can we do better than this? Can we go, say, from an exponential annealing time to a polynomial annealing time, or something else? So this is what our objective was. Okay, so let me talk to you about what the actual model is. It's a fairly simple model. There's not a whole lot of bells and whistles to it. It's essentially a ring of spins, and the spin, or the bonds between the spins, have certain couplings. And when we go into a particular regime of these couplings, then we get this scenario that I sketched out about exponential annealing time. So what we have is we have some coupling capital J on the bonds that are within, say, the bulk of the chain, if you will. And then there's couplings on the left and the right of the chain. So the left has these left couplings, JL, and on the right we have this minus JR factor. So all the J's are positive, but there's a minus sign in front of the JR. And so this is a fairly simple system in terms of like how to analyze this. HP that we have looks something like this. And the idea is that this minus sign on the right of the chain is going to induce some frustration in the system. So it's not so important here to like remember all of these JRs, JLs, and J's. The key thing, for at least for like interpreting the results later, is that if you take a specific combination of these JLs, J's, and JRs, they satisfy some inequality, then you get the scenario where you have an exponential annealing time using the standard linear interpolation. So that's the key thing. There's an exponentially closing gap for the experts where that means something to you. So this is just our system, what it looks like. And I can give you a few pictorial views of like what the ground states look like and the first excited states to get a handle on this. So the ground states are either all in one state or all in the other state, which I've shown as like unfilled and filled circles. And in this case, we can calculate what the ground state energy looks like, and it looks something like this. Again, not so important the exact values. What's more important is that we can calculate this, so we have an idea of what it is. The first excited states look something like this. So you essentially flip a fraction of the spins. So just a visual as to what these look like. And what we see here is we can have we can write down what this first excited state energy looks like in terms of E0. and the other parameters in the model. So the reason I bring this up is just because this is how we look at our figure of merit after we were able to use this analysis to look at the figure of merit. That's the only important thing. Okay, so this is the setup. We have this problem Hamiltonian. It's a simple problem that like we know how to analyze like exactly, like there's analytical results about it. And we know in particular that if you have this exponentially closing gap. So there is this problem if you do standard quantum annealing where you're going to find like an exponential scaling of annealing time with system size. So what we're doing here is seeing, okay, can we take that setup? We know it. Can we use this exponentially closing gap or circumvent it or do something to get a shorter annealing time? So what I'm going to show you here is kind of how we build this A of t. This is for like a specific example that I ran, but it's just it's like more illustrative than anything. So what I'm showing here is going to be the schedule. The schedule is just the A of t function as a function of time where I've divided by the total annealing time, capital T. So it goes from 0 to 1. And our functions are going to start at 0 at the 0, 0 coordinate, and are going to end at the 1, 1 coordinate. So that we end in the our final Hamiltonian is in the is just the problem Hamiltonian. That's the idea. So what we do essentially is we start by choosing three piecewise a piecewise linear function composed of three pieces. So we might pick them randomly between say like 0 and 1, their heights, their y values. Then what we do is we evaluate the energy at the output. So I've shown you here, just to be clear here, dotted line is just showing the linear interpolation between the point and the previous point. And the three light green circles are the random point that we chose, for example. Then what we do is we feed this function, this A of t, into an optimizer for this fixed annealing time, capital T. I haven't shown what the capital T is here, but it's fixed is the point. And then we let the optimizer try to create a better schedule from this like initial seed. And so it might find something, and then and eventually it will converge to some energy that it can't improve anymore. So for example, say for example, we've ended at this point where we have an energy we see here, it's minus 2.3 something, and we can't improve the energy anymore. So then what we do is we insert more points in between the points that we have already, and then we try to optimize those. So that we can improve the energy even further. So like very practically, what this looks like if we did another round of this is it's going to look something like this. So what we've done is we've inserted new points between the previous points and then let all of the points fluctuate so that we can optimize over them. You can see here that the new schedule, the ones where the green circles, the darker green circles, is somewhat similar to the previous schedule, but it's still a little bit different. There are some differences, and you can see, in fact, that the energy does improve as well. So this is good. Now, this energy, it's going to a specific value that we're hoping to get to. Not so important, but just the point is that it's improving. And then we can do it again. And when we did it again, it looks something like this. And then we get an even better energy that we found. So the idea is sort of like iterative improvement. So we start off with just a few piecewise functions, and then we optimize these as much as we can. We insert new points in between the original points, let all of the points be optimized, get a new energy, and then repeat. And we keep repeating this until we either get to an energy that is good and that we actually can, that we're close enough to the ground state for our given tolerance that we're happy, or we find that the energy is not changing enough anymore, and so we say that it's converged and, well, we exit the protocol. So it's one of the two. We either exit early when we're happy with the energy that we get out, or we keep going until there's not enough improvement anymore. So we do this. So this is kind of, so for all of the other schedules you'll see after, this is kind of the base template for what's going on. Okay, so just to give you an idea of what these schedules could look like, I'm going to show you a selection of a bunch of them for different system sizes. And now you can see here on the horizontal axis, instead of just capital T, I've put T min because we're looking at some of the results that I have. So some of the minimum annealing times we found. Oh yeah, and so yeah, of course, the other reason that we use this T min is because as the system size grows, the annealing time also grows, and so this lets us view everything on one compact view. Though of course, in theory, the annealing time is going to be longer for, like I said, bigger system sizes. Okay, so here you're going to have an explosion of functions here to look at, but this is more to get an impression of what kind of results come out. So yeah, like I said, I promised there was a lot of colors, a lot of different functions, and indeed there are. But the reason I'm showing you this slide is just to give you a sense of what kind of schedules we find, and what kind of what happens for these systems. So in fact, these are for the different system sizes here that I've shown on screen. It might be a little bit difficult to connect the specific system size with the right color, but they're all there. And so you can see that depending on which system size you use, there may be more or less points that you end up having. You know, there's little circles on the schedules that show you how many points we have for it. So this really just depends on what happened in the optimization. There's two things that I'd like to kind of bring your attention to. The first is that many of these schedules seem to have this sort of pattern where they start by increasing, then they get to a certain value that's not 1, and then they kind of dip down a little bit and then come back up. If I use my cursor here, it kind of okay, I don't know if this is going to do things really bad, but I have the laser pointer here, so it goes up. So it kind of goes up with a lot of the schedules, then it comes down, and then it goes back up again, all the way to the end. And so the idea here is that, just turn this off. Okay. The idea here is that maybe this is significant in some way. In fact, we haven't been able to like pin down exactly what's going on with these schedules. We thought maybe there was some sort of like template schedule that could be good for all of them, but it turns out to be a little bit more complicated than that, or at least we weren't able to find anything. I did want to point it out though, because it was something intriguing that we did find about the schedules. And in fact, right here, I'm showing you this particular value, A star, and this A star has to do with where the exponentially closing gap is in our system. So this is the value of A, of this function A of t, such that when you're at this value, the time dependent Hamiltonian becomes has this exponentially closing gap. And so what I'm noticing here, at least, is that it seems like all of the, well, not all the schedules, many of the schedules kind of go up towards this A star, then they go away from it again, and then come back and finally cross it at the very end. I bring this up because I'm going to show you some results in a few slides that may lead to some more evidence as to why this could be relevant. But again, this is just something I wanted to point out.
Can I ask a question?
Yes, go for it.
So doesn't A star depend on the system size?
Does A star depend on the system size? This is a good question. I believe. Okay, I'll have to check my notes again. I believe it depends on the on the couplings, at least to a certain order. So I think if you do like an approximation for like where this A star is, I think it really depends on the on the couplings, and it doesn't depend on the system size. But it's a good question. I'll try to get back to you on this. I'll have to check. Because yes, if it depends on the system size, then this is not representative of the situation. I'm pretty sure it does not depend on system size, if I recall. But yes, thank you, Eugene, for the question. I appreciate it. Okay, so now I want to move a little bit forward. So okay, so those are some of the schedules that that we get. But now this is like the main results of our project, is essentially seeing, as we scale up the system size, can we figure out what the annealing time looks like, this T-min. And so we have I'll show you a few different views of what this looks like. First, on like the main figure, I'm going to show you the minimum of the T-min. So like this is, if you do many iterations, many different optimizations over the same system size, what is the best T-min that you find? Because these algorithms are a little bit, well, they're stochastic in nature, depending on what you start off as your initial guess, and these sorts of considerations. And then I'll also show you the median to get an idea of like more of typicality for this annealing. So, oh yeah, one last thing I'll mention before I show you the data is that we did end up going to fairly large-ish system sizes to like, I think it was like the n equals 39, if I recall. And the reason we could do that is because for our particular system, there's some symmetries and some tools you can use from Lie algebras to do the simulation. In fact, this is why Frédéric and Martin were very helpful in this project, since they had some expertise in this sort of area. So they helped out doing these simulations for larger system sizes, or if not, we would have been capped for smaller sizes. Okay, so I'll start with the main results for these minimum annealing times. And so here I've shown you for different C's. Again, these C's are how tight our tolerance is to the ground state. So smaller C means we want the energy to be closer and closer to the ground state. And so these are the optimized results. So when we actually decide what this AFT is. And you can see that even so, it doesn't seem to really matter too much what we use for our tolerance, at least for like these few examples. They all seem to scale sort of the same way, which is, again, this is a semi-log plot. So the curving towards not a plateau, but towards slower growth indicates something that's not exponential. So this is the first part of the results here. The next will be, like I said, the median annealing time, so to give a typicality. And we plotted this as n squared. The reason is that we were looking at this curve on the bottom, or the data on the bottom, and saying, okay, this looks like it's polynomial. And so we were looking for different fits, and the fit that we found seemed to be good with n squared. So if our guess here is good, that n squared is a good scaling, is how the median scales, well, then these should be straight lines. And indeed, this is what we roughly find. Not exactly, but roughly find this. So we see as we grow the system size, that the scaling really does seem to be quadratic in the system size, and this shaded area is some error bars that we defined. So this is just to give a sense of that this scaling really is polynomial in the system size. It's not exponential anymore. And then finally, what we did, I'll just show you on this plot for the last thing to kind of really reinforce these results, is that we looked at what happens if we just do the linear schedule. So we don't do any optimization, we just take a linear schedule and go for it. And well, we couldn't go very far because, well, you can see here that the scaling was not very good. Yeah, so this is for the linear schedule, and this is a straight line in a semi-log plot. So these are exponential in nature. So really, this was sort of like the main thing that we set out to find, is like, could we optimize our schedules and make them work in a way that doesn't scale exponentially? And the answer seems to be yes for our investigation so far. So yeah, so this is what this was like the main thing, our main finding in this project. So that's what we did. This, yes, like I said, this is the main thing we found, but then we wanted to go further with a few things. Like the main thing is that we found all these schedules that I showed you in the previous slide, and we wanted to see, okay, do the schedules mean anything? So like I mentioned before, at first we were thinking maybe there was like some template schedule that that was like good for this problem, and that we could kind of start from there and we wouldn't have to do as much optimization and it would work all the time. This turned out to be more trickier than that. It wasn't as simple, but this sort of questioning led us down to some other questions about the not about the annealing time, but about the quantum state that we get as we do the evolution. And so this is the final set of data that I'd like to share with you. Essentially, what we did is we asked, what happens if we track the optimized the quantum state during the optimized schedule, like its trajectory, versus the linear schedule for a fixed annealing time that is the one that we found from the optimized schedule. In other words, what we were trying to see is, okay, the optimized schedules have smaller annealing times. Why do the linear schedules not work with those smaller annealing times? Like, what goes wrong? And so we track this essentially with the population levels, or the populations of the different basis states of our system. So what we did is we said, okay, how much of the fraction of the quantum state is in the ground state of the instantaneous Hamiltonian, how much is in the first excited state, etc. And we track this as a function of time to see what goes on. So we wanted to see what's happening within the quantum state itself as we do the annealing. So this is the first set of data here. Unfortunately, because of the way I presented the data, you're not going to see the horizontal axis until the end. The horizontal axis is just T over T, the capital T over the annealing time. So this is just what we're using here. So like I said, first thing is the population. So we see here, when I put this data up, that two very different things happen with the population levels. So here I put some data on the side just to give you the idea. Like, this is for the n=9 case. The dashed gray line, this is the function a of t for both cases, linear on the right and optimized on the left. And this a star is again this a star from before. And this is why I was saying this is not dependent on system size, at least at this order. And so yeah, so let me just explain the other parts of this figure here. So the ground state population is in green. The excited state population is in this blue, and excited state starts off at the bottom and green starts off at the top. And we see that there's some very different behavior that goes on here. So you start at time equals 0, you're in the ground state. This is because we start in the driver Hamiltonian's ground state. So we're there, that's fine. But the key difference is that there's different behavior. There's different behavior as to what's happening with the linear schedule versus optimized schedule. In particular, the optimized schedule only passes, so it only has this jump, this transition between states, between like the ground state population and the excited state population at the very end once we cross this a star. And so it has this inversion. And then when you measure at the end, say trying to get your solutions, you're going to have more of the excited state population over the ground state population. Now, of course, from like the particular one I showed here, you still have a finite probability of measuring, say, your ground state. So it's not the end of the world if that would happen, but it was above our tolerance, our C that we defined. So this was not good. Whereas on the optimized schedule side, the ground state population in fact decays for quite a while, and it in fact decays and becomes less than the excited state population until it reaches again this A star where it inverts second time. So it kind of swaps the majority between the excited state and ground state twice, where the second inversion happens at this A star, and then we find that we bring all our population, almost all of it, back into the ground state to finish the annealing. So this is what happens, at least qualitatively, for these two systems. And yeah, one of the key things is that what we've been trying to see is that the decay that happens on the green curve for the optimized schedule seems to happen a little bit because the schedule brings us closer to this A star point. The A star is the vertical sorry, it's not the vertical. The A star is yeah, okay, in this case it's vertical because it's in the same axis. So yeah, it brings us closer to this exponentially closing gap and then moves away from it before eventually crossing it again. So let me just share a few other parts that are relevant to the story here. So if you look at the energy levels, so the energy levels of the instantaneous Hamiltonian, we get something that looks like this for the two for the energy of, say, like the ground state energy versus the excited state energy. And so you can see here for the instantaneous Hamiltonian, let me just get out the laser pointer again to really specify. So they start off far away from each other, the levels, but then they get close around this point here. They go farther away again, and then they come close and really close at this point because this is the exponentially closing gap. But you can see that in the linear case, this only happens once at the very end where they come near each other. And so we think at least that this is significant for why this population, why we're getting the majority of the ground state population at the end. So then what we can do is we can just put the second row of data as a difference to really track what's happening, the difference here, and to really bring out this these parts here, and this exponentially closing gap. And so if I plot this in a log scale, or a semi-log scale rather, then we'll see here that we do indeed find a decay so that it gets smaller. So the two energy levels become close to each other. The populations start to invert. We go away from each other, and then we eventually go and dip back down into the exponentially closing gap. This is the final time it crosses, and then we end up in the for the optimized case in the ground state that we wanted. Whereas in the linear case, you can see that it only happens once. It only happens at that exponentially closing gap. We get close, and then we're done. So these are sort of the two scenarios of what can happen for the optimized case versus the linear case. And so just to show you one more set of data for this for a different system size, just to give you another idea. Here's another one where things are a little bit more things get close and then far apart a little bit more often, but we see the same sort of behavior. So for n equals 13, excuse me, we get close, the energy levels get close to each other here, then they go apart, and then they get close again at the end. And this is why we have sort of this double inversion happening, where we cross here and then we come back up and then finish at the population that we want. So yeah, so this is more of an intriguing aspect of the project. We presented this, we still don't necessarily have like a full explanation as to like what makes the schedules good versus bad, and like how do we engineer these particular transitions to happen. But I did think it was kind of neat that because this exponentially closing gap is there, by doing this optimization procedure, it actually finds schedules that exploit this exponentially closing gap. In fact, this was something one of someone else that I was presenting this work to had mentioned to me, and they thought this was one of the neat parts of the project. So yeah. Okay. So just for me to finish off here, I want to share some of the things that we still like, some of the questions that are still here for us. So one of the takeaways, of course, is that we saw that we can get a scaling of the annealing time that's polynomial, and we changed the fundamental scaling for, say, like the linear interpolation case from exponential time to polynomial time, quadratic time in particular. One thing, though, that I didn't cover here, and we only were able to look at a little bit, are the ultimate resource requirements. So what I mean by this is that it's all well and good that we found that we were able to find schedules that had these nice properties in terms of the total annealing time. But if you have to spend exponential time or exponential resources optimizing for this schedule, well, then all of your gains are kind of lost in the optimization. So you don't want that. What we've found, at least so far, is that this doesn't seem to be a major barrier. The reason we say this is because we put caps on like how much resources, like how many function calls, for example, in our optimizer we allowed. We have like finite resources for like how long we do these computations, and it didn't seem like we were exhausting things. To do a full investigation of this, we would probably have to start looking at quantities like how many circuits did we evaluate to say do this to do this optimization and so on. But it seems like the ultimate resource requirements are not exponential. At least this would be my hunch. That's the first thing. And yeah, the second thing is, like I mentioned on the previous slide, the best schedules that we found seem to exploit the exponentially closing gap. Not all of them, but most of them, or at least not the ones I showed you are the ones that do in particular. And so here, the ultimate goal would be, okay, can we use this to find good designs for other annealing schedules, even for maybe other problems? This is a difficult question. I would like the answer to be yes, but to get there, I think we need more work for sure. So really, what I loved about this project, though, is that because we had this understanding of this particular classical optimization problem, this model that we call the frustrated ring, we were able to use this insight to help us when looking at how to design annealing schedules. So I thought this was pretty neat, and we were able to show, like I said, these gains in the annealing time. So with that, I want to thank you for listening to me and looking at this work. And if you have any questions, if anyone has questions, please, I would be happy to do my absolute best to answer them for you. But thank you.
Great, thank you very much, Jeremy. A round of applause on behalf of everyone on the call. And as Jeremy says, are there any questions?
Yes, so I guess the most obvious question here is that just by spending time around the minimal gap that is exponentially small in the system size, you don't expect to be polynomially preparing or polynomially tunneling to the other state on the other side of this gap, right? You expect to still require exponential time to use this gap to switch your two states, right? So do you have an explanation for how did you get that polynomial?
Okay, so can you specify what you mean here? So you're saying because when you're getting to this exponentially closing gap, you're saying that we should not expect to be able to prepare this state in polynomial time. I'm not sure I fully understand this part of your question.
Well, supposedly, even if you think about things like Grover, right?
Yeah.
So there is an optimal protocol where you spend a lot of time next to the minimal gap. But if the gap is exponential, you still need to spend exponential time there. It's just you lose maybe a power of 2,
Okay. Yeah.
right? So I'm not aware of any example where just by spending time around an exponentially small minimal gap, we can somehow tunnel polynomially.
Okay. Yeah. So this I'm less familiar with. I guess my first question is, would this apply? So for this, of course, we're not going exactly into the ground state, right? There's like some sort of like tolerance that we allow, so we don't go perfectly there. Could this be part of the explanation? Like I confess that I'm not sure what the answer to your question is, but I don't know, like if you do this to some approximation.
Well, so the only conceivable explanation is that, in fact, you have a lot of states next to your ground state, not just the first excited state, and somehow what you actually do is you prepare some superposition of them,
Yeah.
relatively fast, and then that superposition at one annealing parameter somehow becomes your second excited state. Sorry, your first excited state, and at another annealing parameter. So essentially, I guess what I'm trying to say is that there is an effective gap that is not the gap between the first excited state and the second one. But okay, never mind. I actually I actually don't know if it's possible to argue this kind of things just by hand waving.
Sure.
But one thing that you could definitely try is that there are those pause schedules. And you can definitely try to just pause next to the minimal gap and see if that schedule works.
I see. Yeah, I could definitely trust. I mean, thank you, Eugene, for like these comments. I really do appreciate it, because I want to yeah, like any concerns or suggestions you have, I definitely want to take them on board. So yes, thank you for this. I will check this out.
So Viv, I see that your hand is raised, but just while we're on this topic, if I may, I mean, so Julia mentions the possibility of pausing before you go through the minimum gap. But I guess your algorithm would find that if it considers that to be a good thing to minimize the energy at the end of the anneal, then it would automatically keep all your piecewise linear steps of the schedule at the same level. Is that correct?
Yeah, I think, in fact, if I just go back a couple of slides, I think I have, okay, these ones, it doesn't, okay, so what, if I'm understanding what you're saying, it's that this dashed line, you would say that we would pause and stay at a certain fixed level, right?
Yeah, so you're seeing that sort of in the region just after that.
Yeah, here.
It's like a pause to me.
Yeah. So so this pause, I suppose part of it could be that it is finding a pause. Another part of it is that when we choose these points, they're like spaced out equally, and we didn't play with optimizing like how close the points were to each other. So if you played with this, then that could also change, maybe like if it wanted to pause or not, I could imagine. Yeah.
Okay. Viv, over to you. You've been waiting patiently.
So I wanted to ask, the way you showed you were approximating the schedule, you started with a few points and then you doubled them because you put
Yeah.
points in between, then you doubled again as you
Yeah.
put more points in between. So I'm just a bit concerned about the classical resources you're using seem to be scaling exponentially. So as you get to bigger system sizes, you end up needing to put exponentially more points in to approximate those.
So this is a great question. I would so from what we've seen so far, we seem to find good approximations to our ground state without needing like thousands of points. This is what we see so far. But I do agree with you that this is something to check to make sure that the number of points, because when you add in, when you double the number of points, you're effectively doubling the number of parameters that you are varying in the optimization. So making sure that this doesn't get too large. From what we found for our system sizes so far, it doesn't seem to be growing too much. But of course, we can only say so much about like the systems that we have. We have it like up to n equals 39. I mean, you go to 3,000, then all bets could be off. This may be bad. So, but yes, I agree. This is like part of the question in terms of the classical resources pinning this down. So this would be something else to look at. So yes, thank you for mentioning this.
Yeah, and I mean on this slide, for instance, you have ground and first excited state. Does that account for essentially all of the population?
Yeah, you're asking if like the sum is equal to 1.
Roughly speaking, because that was the previous question, was whether you're populating higher excited states significantly enough that your transitions are actually not across the minimum gap, they're actually across a bigger gap, which is, second excited state to ground state, which is going to
okay, I see now. Okay, this makes sense. So for the two schedules here that I've shown, roughly the first excited state and the ground state do make up the total population. I believe for this n equals 13, there's a little bit of higher excited states that do come in, but they come in, I would say, for like they come in at maybe like 0.1 or something of the total population. So it's a smaller fraction. It's not like a huge fraction that are coming in and transitioning. So I would say like mostly from what I've seen for these systems, it's the first and the ground state and the first excited state that make up.
But we're looking at 9 and 13 here. We're not looking at 39 yet. That at those small sizes, you might not see the way that's going to go with the scaling. You're not really far enough for that exponential stuff to be sneaking in behind you. So. And also this problem is not necessary. I mean, it's a toy problem. And it's not actually that hard, so to speak, because it's got a lot of symmetry. So you have to test something like it on a more random problem to make sure there's not a symmetry effect here that's giving you a leg up.
Okay, yeah, this is a great suggestion. Do you have like any particular models in mind when you say like a random model, or is there like something you're thinking of in particular?
There are other gadget ones that are not symmetric that Nick Chancellor has designed, or you can use the Sherrington-Kirkpatrick spin glasses, which properly used, but not all of them will be hard. There's also a curated max 2 set that Elizabeth Crossan has curated that is 20, just for size 20. And Tamim for sure could get you introduced and access to that if you wanted to try that.
Okay, yeah, yes, thank you for mentioning these, because I definitely agree. Like when you're trying to, like, the end goal is not to show something great about a toy problem, but to be able to say something larger about like the broader set of problems that you might encounter. So yes, not getting stuck with any of these extra advantages is definitely a good thing. So yes, thank you for mentioning this.
Thank you. Interesting talk. Nice piece of work.
Thanks.
Good. Yes, thank you very much, Jeremy. We should probably conclude there. Another round of applause from everyone here. And a reminder to all attendees that next week's seminar is, I think, at 1 minute past midnight on the Universal Time Clock, which will be good for people in the Americas and the Far East. And that will be given by Elijah Pavlovsky from Los Alamos National Lab. A lot of benchmarking and comparing QAOA with quantum annealing, for example, which I'm looking forward to. Good. Thanks once again to Jeremy. Thanks to everyone for attending, and we'll see you all next time. Thanks.
Thank you very much. Have a good day.